In this video, we're going to go over the formal definition of the Laplace transform and present some terminology. So our Laplace transform is indicated by a script L. So if we want to take the Laplace transform of some function of time, we would have something like this. So this would be read as a Laplace transform of f of t. And so of course that's going to give us some frequency domain function, which we're going to call capital F of s. So not always the case, but typically we'll have lowercase variables for time and uppercase for frequency domain. So our Laplace transform of f of t, which is equal to f of s, is defined as the integral from 0 minus to infinity of f of t times e to the minus st dt. And to be consistent with the notes, I'm going to label this as equation 1. So we can refer back to that later if needed. Okay, so this is our expression, and we're going to come back and we're going to look at how we can use this to take Laplace transform of specific functions in a couple videos from now. But first I want to talk a little bit about this definition. So one thing to note is this s that we have here and here is not the same as what we have used before when we were talking about frequency response. So here, when we're talking about Laplace transform, our s is equal to sigma plus j omega. And so this is the same way that we'll define it when we're using s in our control systems. But what we can see is that this is a complex value. And so what I mean by that is it has a real and imaginary part. So our sigma here is our real part, and our omega is our imaginary part. And so we can notice that the units of this s, so our s is going to have units of per second. And so the reason we can say it has units of per second is we want this argument of our exponent to be dimensionless, so we have it multiplied by time. So of course, seconds times per second is going to cancel out so that we have a dimensionless argument as desired. So another thing to note about this equation is that this is actually a sort of special form of our Laplace transform. This is called our one-sided or our unilateral Laplace transform. So one-sided or unilateral. And so that's what we're going to deal with in this class. However, it's worth noting that there is also a bilateral Laplace transform or a two-sided Laplace transform. And all that is if we update the limits of that integral to be negative infinity to infinity, then that's going to give us our two-sided or our bilateral Laplace transform. But again, we're just going to be focusing on this one-sided unilateral. So of course, that's why that's the one that's boxed. So speaking of limits, though, I want to point out something else with this lower limit. So something that you may recall from math. Of course, we have 0 minus and 0 plus. And so let me just sort of draw, well, let's draw just a vertical line. So let's say this line indicates where we're at 0. So 0, and let me actually put this right here on top. So our 0 minus would be if we're coming from the left as we approach 0. So we're coming from more negative values and we're approaching 0 from the left. And then our 0 plus would be as we're approaching 0 from more positive values. And so why is that worth specifying? Well, if we have a discontinuity at 0, then we might have different values for 0 minus and 0 plus. So by having this lower limit at 0 minus, we're able to sort of accommodate and take into account any discontinuities at the origin. So let me just sort of put a note here that this means we're accommodating. So accommodating discontinuities at the origin. Okay. So one other thing then about our f of t here. so our f of t in the argument here. So we're inherently, implicitly ignoring it for values of t less than 0 because of this lower limit that only kicks in, only accounts for values greater than 0 minus. So let me come down here and just say that. So we're assuming that f of t is ignored for t less than 0. So assume that f of t is ignored for t less than 0 because we're not integrating over that region. So if we want to not have that only implicit, but if we want to explicitly state that, we can do that in a couple ways. And so the reason I bring this up is sometimes this is done in textbooks, sometimes it's not. So you just sort of need to be aware whether or not it needs to include one of these two methods or not. So we could either say that it's f of t times u of t. And so remember, u of t is our unit step function. And so what that looks like is if we have u of t plotted versus time, here's a value of 1. Basically what this is going to be doing is it's 0, and then here it jumps up to 1, and then it stays at 1. So if we're multiplying our f of t by this, that's of course just sort of passing everything greater than 0, t greater than 0, and ignoring everything for t less than 0. The other way that we can state that is a little more simple. Of course, we could just say that we're considering f of t for t greater than or equal to 0. So there are a little more details in the notes regarding something called convergence. So a function f of t only has a Laplace transform if that equation 1 converges. So it has a Laplace transform, so oftentimes we'll just abbreviate this as LT. And so we're saying it only has a Laplace transform if that equation 1 converges. And so there are, like I said, some details in the notes, and it talks about something called a region of convergence, ROC. I'm not going to go through that in detail in this video. The reason being, all of the functions that we're interested in for circuit analysis have a Laplace transform. So we're not worried about this convergence issued. So let's just say we're not worried about convergence issues in circuit analysis. And so the reason I say that is because anything that we're going to take the Laplace transform of for circuits is going to converge, therefore it will have a Laplace transform. So in the next video, we're going to briefly talk about our inverse Laplace transform, and then we're going to look at how we can use this equation 1 to take the Laplace transform of some common functions.